Welcome students, welcome to the second lecture, Basic Mechanical Engineering. And in the previous lecture, we have studied some basic basic ideas of thermodynamics. We have discussed system and types of systems, etc. in the previous lecture. So in this lecture, I'll give you a brief introduction of some path function, point function, etc. Okay. So before going to that, I'll give you a brief introduction of the thermodynamics. So in the previous lecture, I have already given you what is thermodynamics, and thermodynamics is defined as the science of energy. And the name thermodynamics is derived from two words, therm and dynamics. So therm means heat. In Greek word, therm means heat and dynamics means power. So which simply means that heat energy is transferred to power. Okay, heat energy into power. So which describes the effort to convert heat to power. According to law of conservation of energy principle, energy can neither be created nor be destroyed. So total energy will become constant. Okay. So consider that there is a rock falling off a cliff. So when the rock is at the top, it has a potential energy of 10 units. As an example, consider it has a potential energy of 10 units and the kinetic energy becomes 0 because there is no motion. When the rock throws down from the cliff, what happens? The potential energy reduces because the height changes and the potential energy depends upon the height. So potential energy decreases, and because of the velocity or movement of the rock, the kinetic energy will increase. Okay, so here say that potential energy will be 7 units and kinetic energy 3 units. So that means total energy will become same. So total energy will be 10 units. Okay, and that is the law of conservation of energy principle. And we are in thermodynamics, we are using this principle also. Okay, total energy of the system becomes constant. And there are mainly two types of approaches in thermodynamics, that are classical thermodynamics, which is also known as microscopic approach, and statistical thermodynamics, which is also known as microscopic approach. Okay, so these are the two main approaches of thermodynamics. And what are the classical and statistical thermodynamics? In classical or macroscopic thermodynamics, we are not studying the individual particle behavior. That means we consider the whole system at a whole system and study the temperature, etc. on that system only. We are not studying the individual behavior of particles. Particles means the molecules, etc. That are on the system. Okay. So macroscopic approach is the study of thermodynamics that does not require a knowledge of the behavior of individual particles, and that is known as classical thermodynamics. Okay, so it provides a direct and easy way to the solution of engineering, and we study the pressure, temperature, etc. on the total system only. Okay, but in microscopic approach, we are carrying analysis on the individual molecules, particles, and behavior of each molecules or particles, and that type of analysis is known as statistical thermodynamics or microscopic approaches. Okay, and So in this microscopic approach, we are studying the each and every particle in a molecular level. Okay, the effect of molecular motion is considered in this analysis. So these are the two types of approaches in a thermodynamics. So mainly in these lessons we are studying the macroscopic approach. We are not studying the microscopic approach. Okay. So what are the applications of area of thermodynamics? Thermodynamics can be applied to several areas, and whenever a heat transfer or mass transfer occurred in a particular system, then we can apply the thermodynamics. Okay, so the in our body also it's a thermodynamic system. We can say that it is a thermodynamic system because the body is constantly heating because of the work that is occurred inside the body, and body cells, the transfer of blood from our heart, etc. Because of that, the work is constantly, continuously doing work inside our body. Because of that, heat is generated. That is why the heat is generated. Our body is hot sometimes. Okay, and when fever or any other the discomfort occurred in our body, the body heat doing work again. Because of that, our body heated, and that is why temperature rises while we are not in while sick conditions. Okay, and the applications, some of the applications are the heating and air conditioning systems in our home, the refrigeration system in our home, and the humidifier, pressure cooker, the water heater, and automotive engines like cars, buses, etc. So these are all the applications that we can apply thermodynamics in these areas. Okay, so these are the main common application. And power plants, solar collectors, engines, rockets, jet engines. So many areas are there. We can apply thermodynamics theorems, thermodynamics properties, etc. And so these are the main applications. So thermodynamics can be applied to these systems to better work forward, but the better working of these conditions. And I already said that the human body is an example of thermodynamic system, and we can use air conditioning system, thermodynamics in air conditioning systems, airplanes, car radiators, power plants, refrigeration system, etc. Okay, so these are all work and thermal energy transfer systems. So whenever there is work energy transfer or heat energy transfer, we can apply thermodynamics laws into those areas. Okay, so dimensions and units, you already studied these dimensions and unit, that the length is represented by meter, represented in meter, and that is unit is in m, unit is as represented as m, small letter m, and mass represented by kilograms, kg, and time in seconds, temperature in kelvins. Okay, so temperature is always represented as kelvins in thermodynamic systems, and electric current as ampere, amount of light as candela, amount of matter as mole. Okay, so these are the basic units, and some of the units, that kilo, mega, giga, etc. And when in the negative sense, deci, centi, milli, micro, nano, etc. So these are the units that we are using to represent that quantities: mega pascal, kilopascal, etc. Okay, kilogram, etc. So next one is the state of a system. So in the previous lesson, we have already discussed the state of a system, and state is the physical existence of a system, and state of a system is represented by its properties, and properties are described by and properties are pressure, volume, temperature, etc. So these are the thermodynamic properties. Okay, so state of a system is the condition of physical existence of a system at any instant, and state of a thermodynamic system is described by specifying its thermodynamic coordinates or thermodynamics properties. So at a given state all the properties of a system have fixed values. Okay, so at a given state it has a fixed thermodynamic properties. It has fixed pressure, volume and temperature, etc. Okay, so pressure, volume and temperature, etc. These are the thermodynamic properties, and these properties are used to describe a system. Okay, next one, equilibrium. So what is an equilibrium? So the word equilibrium implies a state of balance. Okay, in an equilibrium state there are no unbalanced potentials. That means there are no unbalanced forces, okay, within a system. A system is in equilibrium experience no change when it is isolated from its surroundings. Okay, there must be no unbalanced force or potentials, anything. Okay, so the system is completely balanced, so that is known as equilibrium condition. So a system is said to be in thermodynamic equilibrium if it satisfies the required conditions. What are that? So if it system is in thermodynamic equilibrium, it must be in mechanical equilibrium, thermal equilibrium, chemical equilibrium and phase equilibrium. Okay, if a system is in equilibrium with these conditions, mechanical, thermal, chemical and phase, then we can say that that system is in thermodynamic equilibrium. Okay, so what are these equilibriums? So when a system is said to be mechanical equilibrium, there will not be any unbalanced force acting on the system, or total force acting on the system is balanced. Okay, then we can say that that system is in mechanical equilibrium. In thermal equilibrium, there will not be any temperature difference throughout the entire system, or the temperature remains constant. Okay, and we can say that that system is in thermal equilibrium, or the state of the system does not so the temperature of the system does not change with respect to time, and we can say that system is in thermal equilibrium. And phase equilibrium, that phase of the system does not change, or mass of each phase reaches an equilibrium level. Then we can say that system is in thermal equilibrium. That system is in phase equilibrium. Okay, and there is a chemical equilibrium, or the chemical combustion does not change with the time. with the time, then that system is in, we can say that that system is in chemical equilibrium. Okay, so there is no chemical actions occurred inside the system, or chemical changes does not occur in the system, and we can say that that system is in chemical equilibrium. Okay, whenever a system has these four equilibrium conditions, then we can say that that system is in thermodynamic equilibrium. So next one is an important one, which is known as process. So what is a process? We already say that there is a state, and state are represented by its properties. Okay, and consider there is a state 1 which has a property pressure 1, P1, V1 and T1, pressure, volume and temperature. Okay, this is known as system A. Okay, and when some change occurs, or pressure varies, temperature varies, and then something occurs on the system, or some energy transfer occur on the system, what happened? The state of the system changes. Okay, so the state of the system changes from state 1 to state 2. So this new state has a pressure of P2, volume of P2 and temperature of T2, etc. And that is known as process. This change of state, any changes that system undergoes from one equilibrium state to another, that is called a process. Any change that a system undergoes from one equilibrium state to another is called a process. Okay, or the transformation from one state to another. So we can see it in this graph. this x-axis property B and y-axis property A. Okay, so this is the state 1, and some process occurs and it has a path. This is the path of this process, and state 1 changes to state 2 through this path, and throughout this path there are some property changes. Okay, so state 1 has a v1 and some v1 velocity 1, and this has a v2 and a v2, like that. Okay, so this is the process path. This is known as process path. If it does not move through this path, it is then the path will become the path there is there isn't any way that the process is happening through this path only. There are so many paths we can draw here. Okay, so whenever a system changes from state 1 to state 2, there are so many paths. Okay, paths are there. Okay, so that is known as process, and process has a path. Okay, the process can be classified into two: reversible process and irreversible process. If all the system and the surroundings comes to its original state, then the system is said to be irreversible. Okay, in the reversible process, restoring its original state by reversing the factors responsible for the occurrence. All the things that have been changed is come back to its original state. Then we can say that is a reversible process. The process that can be reversed without leaving any trace on the surroundings. Okay, so all the reversible processes are ideal process. All the actual processes are irreversible process. Okay, so irreversible process cannot actually exist, because whenever something happened, there must be some small change, and that cannot be reversed. Okay, so in a reversible process is an ideal process. Okay, so in the reversible process, restoring its original state, not only restoring its original state by reversing the factors, but also reversing the factors that are responsible for the occurrence of the state change. Okay, and the process that can be reversed without leaving any trace on the surroundings, because both the system and the surroundings comes to its original state after the process after reversing. Okay, and in reversible process, all the natural processes occurred are irreversible process. The initial state and energies transformed cannot be restored without net change in the system after the process. Okay, so we have to do some change. So the system undergoes some changes and it cannot be reverted back to its original initial condition, and that types of process are known as irreversible process. Okay, so these are the two types of processes: reversible process and irreversible process. So in this figure we can see that this is an P and pressure volume graph. Okay, the y-axis pressure and this is volume. Okay, and one is the state 1 and 2 is the state 2. Okay, when 1 changes to 2, okay, through this path, clear, and if we said that this is a reversible process, that state changes from 2 to 1 to the same path, then we can say that it is a reversible process. If that process changes from 2 to 1 through this dotted path, then we can say that it is an irreversible process, because some changes are happened there. Okay, already happened there. So in reversible process, two states can be shown by continuous line. Okay, so if the process change happened through this continuous line, then we can say that it is reversible process. If it is happened through this dotted line, we can say that it is irreversible process. Okay, reversible process are ideal processes. Irreversible process is usually represented by dotted line joining the end state. In a real process, the intermediate state points cannot be located. Okay, that means if the system and the surroundings changes from 2 to state 2 to 1 through the same path, then we can say that it is a reversible process. If it is not, then we can say that it is an irreversible process. So next one is a very important term, that is path. So I already said that if a system changes from 2 to 1, we can draw so many paths. Okay, that 2 to 1 can happen through path A, path B, path C. Okay, so the series of state through which a system passes during a process is known as, is called path of the process. Okay, a series of states through which a system passes during a process is now called a path of the process. The series of state through which a system passes during a process is called path of the process. Okay, so consider this system, that this is a piston here, and when we apply some force here, what happened? The volume of the system changes. Okay, volume changes from V1 to V2, and when volume changes, what happened? The pressure of the system increases. Okay, so volume decreases and the pressure will increase. Okay, so here this is the initial state and this is the final state, and this change occurred through this path. Okay, this process occurred through this path. Okay, and that is known as path of the system. Okay, path of the process, not system, path of the process. Okay, to describe a process completely, one should specify the initial and final state of the process, as well as the path follows and the interaction with the surroundings. Okay, so process, if you want to describe the process completely, one should specify the initial state, final state, and then path. Okay, then only we can describe the process completely. Okay, so that is an important aspect in thermodynamic approach. This is the path. So next one is a path and point function. If the value of the thermodynamic variable, depends upon the path followed in good going from one state to another. If the value of the thermodynamic variable depends upon the path, then we can say that it is a path function. If that variable changes from path A, path B, and path C, or that variable is different in path A than path B, path C, then we can say that variable depends upon the path of that process. Then we can say that it is a path function. If the path functions are not properties of the system, mainly two types of path functions: work and heat. Work and heat are path function, or it depends upon the path of the thermodynamic process. Okay, the path function is represented as delta. So work and heat are the two main path functions, and if you want to find the total work done on a system, then we have to integrate from 1 to 2. So W1 to 2 is the work done from changing 1 to 2, changing from state 1 to state 2 through some path. So like that, heat, change in heat, delta Q can be written as Q1 to 2 through some path. Okay, so work and heat are two path functions, and it depends upon the path in which the process is happening. And point functions, properties that does not depend on the path followed, that is known as point functions. So point functions are pressure, volume, temperature, density, enthalpy, entropy, etc. These are the point functions that does not depend upon the path. If the path is changed, that properties, that functions does not change. It only depends on the status. That state 1 has some properties and state 2 has some properties, if whatever the path followed. Okay, that type of functions are known as point functions, and point functions are properties of the system. Okay, path functions are not properties of the system, and point functions are properties of the system. Okay, so we already said that. So these are the important things: process and path functions and point functions. So these are the things you have to study in this lecture and make a notes and try to understand these things. Okay, so that's all for today, and we can see in the next class.